All right, welcome back to the Mathematics of Data Models, Lecture 18. This is a Northeastern University course called CS 2810. And this is Professor Wu. And, well, today we're going to continue with our Mathematics of Data Model, and we're going to learn the concept of covariance and correlation. I don't think we're covering this today. So, very often in science, we need to study the relationship between two factors. For example, here is a plot between income and health outcomes. From this, you are seeing that as the income goes higher, it appears that the health outcome has a positive trend of also going higher. Now, this is called a scatter plot, and by looking at the scatter plot, it gives us a lot of information whether there's a statistical dependency between income and health outcome. So, in this particular case, we are seeing where one goes higher, other also goes higher. This is called a positive relationship. So, this is a positive relationship or positive correlation. In other cases, where when one goes up, the other goes down, that's an example of a negative correlation. So here is an example of amount of hours you exercise and then your resting heart rate. So when your resting heart rate is low, it implies that your heart is pumping blood very efficiently. So your body is doing a good job. So as you exercise more, you're becoming more and more efficient, right? So your resting heart rate is lower. In this particular case, right, one goes up, other goes down. This is a negative relationship or negative correlation. So you can have a positive one, like I just showed you, and we have one where it's negative. Here is yet another one: sugar consumption versus tooth decay. So you can see that there's kind of a positive trend where the more sugar you eat, the more likely you will have a tooth decay. So in scientific research, this is what we do. We gather data, like if there are two factors, right? We gather the data and then we can plot these points out. By looking at these points, we can perform regression, which is you essentially draw this line. And with the regression, you can also produce a number that essentially tells you how dependent the two variables are. So this is what we're going to learn today. Now, there are various kind of relationships that we can observe. We just saw the positive and the negative one. In those both cases, they are both linear relationship, meaning that you can use a line to essentially describe the relationship. Of course, there are also nonlinear relationship. When you have nonlinear relationship, it means it's not really described by a line, but maybe a curve. Here's another example of perhaps a nonlinear relationship. So the last one is when there's no relationship. So the way you can think of relationship and dependency is by drawing the plot into four quadrants. For example, like this, right? Where this line is the middle, is the average x. And this line here is the average y. Okay? So with a negative dependency, which this is a negative dependency, notice when the values of x are above average, the values of y are below average. So this is a very distinct pattern of negative. So x is above average. Notice in this quadrant, all the x values are above, this is the average, so above the average. And yet in this quadrant, all the y values are below the average. Also, if you're in this quadrant, what you have is all the x values are below and all the y values are above. So this is a very distinct pattern that you will see for negative correlation, is that one is above, the other one is below, and when one is below, the other one is above. So that's the pattern. That's the pattern I want you to pick up on. Now that's negative. Positive. So let me write this down. For negative, one is above, then the other one is below. And if you have one below, then the other one is above. So that's like this opposite relationship. Positive, if you draw the middle line here, right? If one is, and here's the x bar and y bar, that's the average. So positive relationship means that if one is above, right? If a point like this one is above the average, for y, it's also more likely that it's above the average. So if we draw this out, positive, we end up with one is above the average, the other one is more likely to be above the average. Conversely, if one is below average, the y value will also be below average. So these are the patterns that essentially tells you whether there's a positive or negative relationship. Right? Now over here is a negative relationship because you can see if one is above, the other one is below. Okay? Now over here, there is no relationship because when one is above, the y value can be below or above, right? Equally likely seems to be. So by knowing x that it's above, it gives us no information about y. It could be above or below. Conversely, like over here, if we know that an x of value is above, it tells us that there's a very high likelihood that the y value is below the average, right? So when you have dependency, it means knowing one tells us information about the other one. Over here, positive relationship, you know if its x value is above the average, it means the y value is likely going to be above the average. So over there, when there's dependency, right, then you know that knowing one variable, it gives you information about the other variable. When there's no dependency, knowing one is above the average doesn't tell you whether y is going to be above or below. It could be either one. Okay? Now, to measure how dependent x is versus y, right? We came up with a way to reduce it down to just a number. And one is called covariance. We can use covariance to essentially measure the dependence between x and y, right? Or we can use correlation. And we're going to go over both of them. Why sometimes we use covariance and other times we might want to use correlation. So, covariance. Well, over here, I have previously made a very specific point, right? The key you want to look at is whether you have a pattern that one is above, others were above, or one is above and y could be anything. Okay? So if we were to look at these two, if we calculate the covariance between this, we're going to get 1.06. So 1.06. And then if we calculate this one, it's 0.06 minus. So notice there's obviously a high dependence here. You can see that. And there's not that much dependence. So when you calculate covariance, right, you're going to get a large value when there's actual dependence. And you're going to get a value near 0 when there's not much dependence. So we previously went over the equation for variance, right? So variance, if you remember, the variance measures on average, how far samples are away from the center. So if on average the samples are very far away, then you have a high variance value, okay? And the way we measure it is essentially we take the value and and measure the distance from the center, square. I hope you remember why we squared it. We squared it so the positive and the negative distance won't cancel each other out. So we take each value and then subtract the mean square, and then we find the average. So we're finding the average distance square, okay? And therefore is x minus mu square, so it's x minus mu, okay? So the idea of variance is measuring how far samples on average are from the center square. Now covariance has a very, very similar equation. Instead of x minus mu, covariance of xy is x minus mu, y minus mu. Okay? Now you might be wondering, okay, so it's x minus mu, so x above the center and y above the center. Why would multiplying them together give us information about their dependence? Right? If you just look at it, variance makes sense because you're trying to find the average of the distance from the center squared. But over here, you have x and you are multiplying by y. Like, how is this right here telling us whether knowing x tells us anything about y? Well, it does. Let me explain. So the intuition, right, is if you let's draw the quadrants again. Right. And here's the center. So this is a positive relationship. And this point, this is the center point. Well, if xi is greater than the average, then xi minus the average must be a positive value, right? This must be a positive value. Similarly, if a y value, and this is y bar, y value is greater than the average, then you should also get a positive value. So all I want you to realize is whether you're going to get a positive or negative. So the pattern with this, especially a positive relationship, is when one is positive, the other one should also be positive. Okay? That means you're like, when you have lots of positives here, they're going to add up to be a large number. Now, this pattern, if you have one value that's below, the other is below, right? So if it's xi is below the average, then you're going to get a negative value. Similarly, yi minus the average should be a negative value. So negative, negative. So when you have negative times negative, is once again a positive value. So what this is saying is, if you have a positive dependence, you're going to have their product, the multiplication of the two of them, going to be a lot of pluses in there, right? Because positive times positive is going to give us a positive. Negative times negative is going to give us a positive. So if we have this relationship, they're all going to be positive and they're going to add up very quickly, if that makes sense. So you're going to get a large positive value. Now, we can use this exact same logic and apply it to a negative relationship. So let's say we have data that looks like this, right? This means that when x is greater, xi is greater than the average, xi greater than the average, is going to be a positive value, right? It's going to be greater than 0, give us a positive value. And when that's the case, we tend to have y I minus y bar to give us a negative value. So notice, because yi is below y bar, so this is a negative value. So when we have positive times negative, it's going to lead to a negative. All right, so that's for this region. What about this region? Well, in this region, what we have is xi minus bar should be a negative value, right? Because over here, since xi is below x bar, you should get a negative. And if you have yi minus y bar, you should get a positive value. So in this case, you're going to get a negative and a positive. Also give us a negative. So the logic here is saying that when you have this pattern, you're going to have lots of positive values adding up. And when you have this pattern, you're going to have lots of negative values that add up. And when we find the average of that, right, average number of positive value, average number of negative values, this pattern will give you a large positive value, and this pattern will give you a negative, right? Also, if you had this pattern, then the positive and the negative will cancel each other out and essentially give you 0. Okay, so following this intuition, let's say we have 4 data sets, and we're going to look at x and y. Well, notice, like I told you, x and y, when you check whether it's positive or negative, so x and y has a very positive relationship, which implies when one is negative, other's negative. So this gives you a positive. When one is positive, the other is positive, another positive. Negative, negative, positive, 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 positive. So it adds up to 6. So you see how this gives us a lot of positives. Okay? So that's an example, x and y, to be one that has very high dependency. Now here's an example where you have low dependency. When you have low dependency, sometimes it's positive, sometimes negative. Notice how these are positive, this is negative, this is negative. So when you have low dependency, it means the positive and the negatives are canceling each other out so that you kind of approach 0. So last one was 1, right? So that's very high. In this particular case, because the positive and the negative are canceling each other out, you don't get 1. You get something much lower. Okay? Also, this is an example of a negative dependence. Notice how when you multiply them together, you just end up with lots of negatives. And therefore, when you have lots of negatives, then you get a large value, but negative dependence. So that is how covariance measure dependence. It's subtracting the center for one value and subtracting the center for the other variable. And if one is positive and the other one is also likely to be positive, it tells you that the trend, it tells you that one is, by knowing x, you also have a high chance of knowing y. Okay? All right, so why don't you pause the video, and given this data set, see if you can calculate the covariance. Okay? Calculate yourself. Pause the video. We'll move on to the next thing. So the solution is here. If you want to double check whatever you did here to make sure you got the same answer. Now, we just talked about covariance, and covariance essentially reduces 2 variables into a number, and this number tells you how dependent they are. And when we talk about the concept of dependence, in this context, it's telling us that if we know one variable is above average, it gives us information whether the other variable would be above or below average depending on their relationship. Okay, so but so we that's covariance. But now if I show you two data sets, one data set looks like this, and the other data set looks like this. The only difference is that some of these are multiplied by 100, so they're much larger. Therefore, therefore, when we calculate covariance for this data set, this is the covariance, and for this data set, the covariance is right here. So it's scaled by 100. Well, this is a problem because depending on the scale of your data, you can get a covariance that's very large or the covariance that's very small. And by looking at purely the value of covariance, how would you know whether this is a large or a small covariance, right? Like maybe this is a large one, or maybe this is a large one. You don't really know. So covariance is useful in telling us, like, compare to three distributions, which one are more dependent. But if we just want to look at the absolute value of covariance, the number is very confusing. Like you don't know if this 0.666 is a large value because your data can always get scaled smaller, right? So that is the problem with covariance. You get a number, but you don't know if that number is considered large or small. And this is why we don't use covariance when we want to report the dependence. We want to use correlation. Right? So the correlation, also known as Pearson correlation coefficient, the R value. And it's very easy actually. Correlation is simply a covariance. So we learn how to calculate the covariance. So it's just a covariance divided by some number that guarantees the value to be always between 1 and -1. That is covariance. That is correlation. So correlation is just covariance, which you learn how to calculate, divided by some number. And if we pick the right number, the correlation should always be between -1 and 1. And now, this is an absolute. We know the number can never, ever, ever be greater than 1 or less than -1. Therefore, if we see a value that's 0.99, we know that this is very, very high dependence because it's close to 1, right? And if we know a value that's roughly 0.4, we know this is a weak dependence because compared to 1, 0.4 is a lot smaller. Okay, so anyways, the key here then is if we know how to calculate covariance, how do we know what number we divide? What number do we divide to guarantee that we are scaling the covariance to be between -1 and 1? Okay, so the key here, after we know what a covariance is we want to know how to find this magical number. Now, how is that correlation could be always between this? So let's look at some basic facts. We know that covariance is between the dependence between x and y, right? So you're measuring the dependence. So you're assuming that x is not the same as y. So this dependence depends on x, y. No matter how high, their dependence can never be greater than the dependence with itself. So you can depend on your friends, but you can never depend on your friends more than you can depend on yourself. That's what this is saying. You cannot, the dependence is as high as it gets, right? Remember how we calculate covariance. If one goes up, the other one goes up. Now, if you have XX, well, if one goes up, X is the same as X, so the other one has to go up. So that's the perfect dependence, right? So what we are saying, and remember, covariance, I don't know if I told you guys this. Covariance of x, well, if you look at the equation, this becomes the variance of x. I think by looking at the equation, you guys should have known this, because right here, covariance is defined as x minus x bar, y minus y bar. But what if y is equal to x? Therefore, notice how this and this becomes identical. So the covariance of xx is just the variance of x. Okay? Okay. So my point here is no matter how much x and y are dependent on each other, right? Their dependence can never be greater than xx or yy, right? Yy is the largest dependence. And from this observation, we can conclude that xy is always less than xx, and xy is always less than yy. Okay? So this is what we can conclude. And after this conclusion, we can divide both sides by xx and yy. So notice, if we divide the covariance by covariance of xx, it has to be less than 1. Okay? Look at it from here, how we got at this point. Similarly, we can divide both sides by the covariance of yy, and we got another relationship. So we know that essentially we can divide the covariance by covariance of xx or the covariance of yy, and the value will always be less than 1. Okay? Now next, I want you to note 2 specific facts. One is that if you have 2 numbers that are less than 1, when you multiply them together, they will always still be less than 1, right? So over here, 0.5, 0.5. They're both less than 1. So if you multiply them together, their result will still be less than 1. Okay? Over here, you have a value that's equal to 1, but this is less than 1 multiplied by this. It's still less than 1. So if you have 2 numbers that's less than or equal to 1, their product, when you multiply them together, the result will always be less than 1. So that's observation number 1. Observation number 2 is that the square root of a value less than 1 is always less than 1. So for example, take the square root of this number, 0.8. Well, the square root of a number less than 1 will give you a number still less than 1. So that's the second observation. Now, if we can combine these 2 logic with what we just discovered, well, we know this is less than 1 and this is less than 1. This means that if we multiply the 2 together, the result is still less than 1. That was from rule number 1. So if we just multiply them together, the result is less than 1. Well, when we multiply 2 of them, that's a square, right? Now, the second rule, we can now take the square root of this. If we take the square root of this, guess what? The result of a value, if this is already less than 1, then you take the square root. The result is still going to be less than 1. Okay? So now I take the square root. The result is still less than 1. Well, from here, the square cancels out, and now you just have the square root of the covariance x, covariance y. And because it's a square root, it's guaranteed to be less than 1 and greater than negative 1. Now, you may remember I told you the covariance of xx, right, is just the variance of x. And covariance yy is just the variance of y. And if you take the square root of each one of them, the square root turns out to be the standard deviation, STD of x, STD of y. Or, let me just write covariance of xy divided by sigma x, sigma y. So these are the standard deviation. And this is the equation for correlation. Relation. And this, by calculating this right here, you can calculate the value of correlation that measures the dependence between two variables. And when you, after you measure the dependence of two variables, it's always going to be between -1 and 1. Therefore, you have an absolute reference point to say 0.9 is a pretty high number because it's close to 1. Okay, at this point, why don't you pause the video and see if you can calculate the correlation for this particular example. Okay, after you pause the video, you can always check your answer right here. Now, when you want to calculate two data sets, this one and this one, and you want to calculate the covariance, the NumPy command is really easy. It's just cov. So the covariance, right, instead of giving you just one number, in NumPy, it gives you a bunch of numbers, right? So if you have x and y, it gives you it gives you a matrix where you automatically calculate the covariance of xx, covariance of xy, covariance of yx, covariance of yy. Hence, you see 4 numbers. So this essentially tells you all the possible covariances. Now correlation also gives you a matrix, similar idea, except over here, right, this is the covariance of xy. So this is going to be the correlation of xy. And correlation with itself is just 1 because that's as high as it gets. So you can calculate covariance and correlation, use NumPy with these commands. Okay, now a high correlation does not imply causation. So here's an example. Total amount of ice cream sold at the beach, and then number of drowning. So what, based on this data, what it's saying is that the more ice cream it's sold is highly dependent and gives you information about the number of drowning. Now, just because the dependency is very high, it doesn't tell you, it doesn't mean that the ice cream sold is causing the drowning, right? There's a separate factor, and we call that factor the confounding factor. Okay? So if you don't have the confounding, just because there's a strong relationship, it doesn't mean that one is causing the other. And for this particular case, you might guess that there's a third factor that's actually causing both. It's just hot weather, right? Because it's hot weather, it's causing more people buy ice cream, and it's causing more people to be at the beach and near the water. So this is very interesting because for the longest time, right, oil companies can essentially deny the fact that their activities are causing global warming, because mathematically speaking, it is true. Just because you have increased oil activity and digging, and that the climate is getting warmer, it doesn't mean that one is causing the other. And, mathematically this is true. And this happens to be a very, very convenient argument. Similarly with smoking, even though there's a very, very strong indication that the more you smoke, the more likely you're going to get lung cancer, but because this is like one part about correlation that's really, really faulty, is that just because the more people smoke, the more lung cancer, you cannot definitively and mathematically say that smoking is causing the lung cancer. So correlation is great. It tells you that there is a lot of dependence. And now that you know the mathematics, all that it's saying is that if one is above the average, the other one is more likely to be above the average. But that cannot tell you whether whether one factor is really the cause of the other. All right, so for the last practice, over here I want you to calculate correlation. Right, take these points. This is the data. Right, you're conducting a study to see if the amount of time spent studying for an exam is related to the final score. And you collect the data for 5 students and you plotted their study time versus grade. So this is study time versus grade. I want you to use these data and calculate the correlation, and then use Python to confirm your correlation. And after that, you want to essentially draw a line, right? Remember in the very beginning, every single research, they always draw a line. Wait, over here. Right here, right? Every research, after you plot out the data, they always draw a line. Well, now you know how to draw this line. This is essentially the linear regression that we learned. And after you draw this line, right, and you have the correlation, you can essentially, based on the correlation, report if there's a strong relationship between studying and getting good grades. Okay? So that's it. This is the video for today. I will see you in the next lecture.